Hello, this is Yan. Today I'm going to talk about geodesy. So first, from today's lecture, we will learn what is geodesy and what can geodesy do in both scientific research and in our daily life. Then I will introduce two popular geodetic tools. One is the Global Navigation Satellite System, GNSS. Many of you may know GPS, which is one of the GNSS. Then I will introduce interferometric synthetic aperture radar, INSAR. So from its principle to application. So first, let's watch a video to learn what is geodesy and where can we use it.
You may not know it, but the study of geodesy probably impacts your everyday life. Now I know what you're thinking. What is geodesy? Geodesy is a field of science concerned with measuring three properties of Earth: its shape, its orientation in space, and its gravity field. These properties change over time, so it's important that scientists are keeping tabs on Earth's overall position, as well as the position of its major parts, such as continents, oceans, ice sheets, volcanoes, and more. High-precision GPS instruments can record millimeter-scale movements, even over long time frames, which enables scientists to detect seemingly small changes to Earth's major features, small changes with potentially hazardous consequences. So now that we understand how we obtain this data using geodesy, let's take a look at how we apply these tools in everyday life. The accumulation of magma in the shallow chamber below volcanoes causes the Earth's surface to actually inflate, deflate, and deform with changes in volume. By monitoring ground deformation in active volcanic zones, we can begin to understand the complex plumbing that lies below volcanic features, and hopefully forecast volcanic eruptions. Believe it or not, the Earth's surface also moves up and down during periods of drought. When water is present at or below the surface, the weight pushes the ground downwards, but when this water disappears, the surface begins to rebound. Entire mountain ranges like the Sierra Nevada grow and shrink by several millimeters just from changes in water. High-precision GPS and remote sensing can be used to monitor these small changes and in turn monitor drought progression and recovery. Geodesy is also used to monitor polar ice. Scientists use a variety of tools, including GPS and LiDAR, which stands for light detection and ranging. LiDAR is a remote sensing technique that uses a pulsed laser to measure distances between the laser source and the Earth's surface. By isolating various data points, we can generate precise 3D models with a range of applications. In this case, we can monitor changes in glacier speeds, depth, and extent. Satellite measurements can be used in a number of ways to better understand and respond to devastating earthquakes across the globe. For example, geodesy can be used to quantify ground surface ruptures and identify rockfall hazards. Additionally, remote sensing can be used to detect communities that suffered the greatest damage and deliver aid resources by priority. Geodesy can also aid in the response to man-made disasters like oil spills. Using remote sensing technology, we can detect oil spills in real time, hopefully preventing some serious ecological damage. GPS data allow optical remote sensing information to be linked with geospatial data, so scientists know exactly where an oil spill has occurred and how best to clean it up. Satellites and remote sensing also have uses in agriculture and forestry. Using this technology, scientists can analyze vegetated areas to assess the overall health of the plants and the soil. We can observe the visible and near-infrared wavelengths reflected by plants to determine the chlorophyll content. In addition, a specialized NASA satellite has been deployed that can measure soil moisture from space. These data produce global soil moisture maps that help us better understand the health of our world's fertile lands. GPS provides another essential service to society: timing. GPS satellites contain atomic clocks, which can relay super accurate time information to people who need it most. World financial markets, power grids, and hazard communication systems all rely on GPS data for precise timekeeping. GPS systems are key to safe navigation, and with the world of autonomous vehicles on the horizon, the precision and reliability of GPS nav systems is paramount. Personal vehicles and commercial fleets will rely on this information to determine their location and their position relative to other objects on the road. Last but not least, geodesy is also used to measure gravity. When the mass of an object increases, the gravitational attraction of that object increases as well. And because Earth's surface is not uniform, neither is its gravitational attraction. NASA has deployed 2 satellites that orbit the Earth in unison. In response to variations in Earth's gravity field, the distance between these 2 satellites will change, allowing scientists to measure Earth's gravity anomalies. These precise measurements of our planet's gravity are used to determine global sea level, an extremely important reference used in everything from construction to climatology.
Now, let's start with the Global Navigation Satellite System, GNSS. So, our smartphone usually tells us our location in an accurate about 1 to 2 meters. However, the deformation of a volcano may be in a scale of millimeters. So we cannot use our smartphone to measure the volcanic deformation. So here, let's talk about how we can use global navigation system to measure the millimeter scale deformation. A GPS satellite is usually a car-sized object that are placed in orbit about 20,000 kilometers above our heads. The satellite broadcasts radio waves, which is electromagnetic waves. By measuring the time the signal travels from the satellite to the receiver, we can calculate the distance between the satellite and the receiver. The satellite navigation system is basically a timing system. Each satellite is carrying its own atomic clocks. So now you know why theirs has the size of a car. So here is one question. How many satellites do we need to get the position? If we know the distance to one satellite, we can know we're at somewhere a surface with the radius of the distance. If we know the distance to 2 satellites, we know we are at a circle determined by the intersection of these 2 spheres. So if we know the distance to 3 satellites, we know we are at 2 points determined by the intersection of these 3 spheres. So one point is usually in the space, so we can basically know where we are. However, considering we don't have an atomic clock in our receiver, so we need a 4th satellite to correct the time of our receiver. Therefore, we can know our relative position to those satellites. We also need to know the position of those satellites relative to the Earth. The satellite basically will broadcast the orbit parameter of those satellites. So our position relative to the Earth can be obtained as well. So now let's see how we can get the relative distance from the receiver to the satellite. The signal from the satellite includes a piece of code add on a carrier wave here. So for the GPS on our smartphones, we only need the information from the code signal. We don't need the carrier wave itself. The travel time is determined by comparing the signal from this repeating pseudo-random code, which is generated by the satellite. And those codes can be compared with the same code generated in the receiver, for example, our smartphone. The accuracy of the distance between you and the satellite is determined by the physical length of the signal divided by 10. If we use a pseudocode whose wavelength is about 300 meters, therefore the accuracy of the distance is about 3 meters. If we have more navigation satellites, for example, 10 or more than 10, we can get an accuracy about 1 to 2 meters for positioning. However, this accuracy is not enough for us to study the crustal deformation. So we need to use carrier wave, since it has a shorter wavelength. So okay, now is a question for you. What is the typical wavelength of the carrier wave we need if we want to measure like 2 millimeter ground deformation? Here is the answer. To obtain an accuracy about 2 millimeter, we need the wavelength of the carrier wave to be 20 centimeters. The positioning using the carrier wave called carrier phase positioning, which is more elaborate, but also need more observation time to obtain the desired accuracy. So for the pseudocode positioning, the time required is about a few minutes. However, for carrier phase positioning, it requires about hours to days to get the accurate position. There are many sources of errors causing an inaccurate positioning. First, errors may come from satellite itself due to the orbit perturbation or clock error. Second, the travel time can be delayed due to the electromagnetic waves are dispersed or refracted in the ionosphere or troposphere. So in cities, the error may also coming from the multiple reflection due to buildings and the interference from other EM signals. Finally, the error can also come from our receiver as well. The errors from atmospheric delays can be significantly reduced by the model of atmosphere. The errors from satellite receiver can be removed by using a technique called differencing. A single difference can be formed by differencing the measurement required by two receivers, getting the signal from the same satellite at a given time. Single difference between two receivers virtually remove all satellite-dependent errors, such as the satellite clock error and the orbit errors. On the other side, a single difference can also be acquired by one receiver with two satellites. So this is called single difference between two satellites, which can reduce most receiver-dependent errors. So similarly, we can use two receivers with two satellites. So that is called a double difference. It's formed basically by differencing two single differences. So the double differencing can remove most errors from satellite and the receiver. There are also other methods, such as like a triple differencing, which has a similar idea, but you need more satellite and receiver pairs to do that, and it takes longer time to get the result. Okay, if we get the accurate positioning of the GPS receiver, we can use that to measure the deformation of the crust. So for example, when a volcano deforms, the position of those receiver also changes. So we can get the displacement of the volcano by putting several GPS receivers at different locations on a volcano. Here is an example. This is the surface displacement obtained by a GPS network on the Laguna de Moli volcano. We can see the moving of each GPS receivers during the volcanic activity. So this is the horizontal component, and this is the vertical component. Note that the arrow in vertical component of displacement by GPS is usually larger than the horizontal component. The reason is that because the vertical accuracy is worse than the horizontal, since the GPS receiver cannot see below the horizon. So with the deformation information gathered by the GPS, we can model the deformation with some models. So here is an analytical model, and we can use that to study the dynamics of volcano. Okay, now let's go to the second part, which is the INSAR. First, let's take a look at a short video to show you how we get the SAR image.
but today I'm going to talk about a technique called INSAR. INSAR is an abbreviation that stands for Interferometric Synthetic Aperture Radar. And in this movie, I will try to explain the basic principles of INSAR, starting with radar. Radar is an active remote sensing technique, which means that a satellite sends a signal to the Earth and picks it back up. This signal, when we look at the electromagnetic spectrum, is a microwave, because a microwave can pass through clouds and can be used at night. So radar tries to measure the distance between a satellite and the Earth. This by measuring the time and by knowing the speed of the signal. If we combine this, we can measure the distance. Synthetic aperture. We start in the world of photography, where the sharpness of a picture is determined by the opening of the lens, and this is called the aperture. With INSAR, the lens is an antenna, and the sharpness is determined by the width of the antenna, which means we would need a really wide antenna, which is impossible. That's why there is synthetic aperture. When we look at the satellite at two different moments along his path, we have the physical antenna on the satellite itself, but we can also create a synthetic antenna between the two different positions. Interferometric. We first take a deeper look at the signal. We have the amplitude of the signal, which gives us amplitude image, where we recognize some topography. Then we also have the phase image, which looks like random noise, but if we combine two phase images, we can create an interferometer.
The video introduced how to get SAR data, and we can use phase information generated from the SAR to obtain the interferogram. The principle of interferometry is similar to what we see in a piece of oil film. In an oil film, the phase delay is due to the light traveling slower in the oil than the air. And for INSAR, the phase change can be due to the change distance between the surface and the satellite. The total interferometric phase is generally contributed by four components. The first one is the range displacement in the radar target, delta R, which is the information we want. And the second component is the phase difference due to the topographic distortion, since the viewing angle between the two satellite visits are slightly different. And the third component is the phase change due to the atmospheric efforts. So the final component is the noise due to the satellite. To remove the phase change due to the topography, we can model the interferogram according to the DM model. So by subtracting the model phase change from the original interferogram, we can remove the effect of topography. And similarly, to remove the phase change due to the atmospheric delay, we can model the interferogram according to the atmospheric effects, such as water vapor. And by subtracting the model phase change from the original interferogram, we can remove the effect of atmosphere. And the random noise is hard to model, but it can be moved when we combine multiple interferograms. We can talk that later. So here, when we get the phase change due to the range change, we need to convert the phase change to the rate change, since the range change is the information we want. That process is called unwrapping. So here is an example from the three sister volcanoes. Two SAR image, one from 1996 and other is 2000, create this INSAR pair. And those colored fringes demonstrate the phase changes. So we can see from the color bar here, when the color changes from blue to green, then to yellow, and finally to red, which means a full cycle of the phase change. In the image, we can see that from the center of those fringes, the color is changing from yellow to red, which is about half of the cycle. Then is from blue, green, yellow to red, which is full one cycle. And then another 2 full cycles. So it means the range change is about negative 3.5 cycles. Since from blue to red is positive, while from red to blue is negative. And each cycle represents the phase change of 2 pi. So we can use this equation to calculate the range change. So which is 3.5 times 2 pi and then divided by 4 pi and then times 5.66 centimeters, which is the wavelength of the radar wave. And finally, we get the result is about negative 10 centimeters range change. That means the range is shortened from 1996 to 2000, which means the surface got closer to the satellite. So the volcano actually uplifted. Okay, now let's do an exercise. Similarly, we can get the range change is about negative 8.5 centimeters and the volcano was uplifting. Okay, the wavelength of the radar wave used in INSAR not only controls the relationship between the phase change and the range change, what we have talked about above, but also it will affect the coherence of the interferogram. So in order to get the interferogram, we need the radar wave to shoot the same target for the 2 visits of the SAR satellite. So if the radar wave is reflected by a rock, the object does not change a lot between these 2 visits, so we can get a coherent interferogram. However, if the radar wave is reflected by a tree, it's very likely that during these 2 visits, the tree has already changed a lot. That means there is no coherent interferogram can be obtained. So generally, the radio wave with longer wavelengths can see through the vegetations like L band, while the radio waves with shorter wavelength like X band will be reflected by the leaves of the rock, of the trees. So to study the crustal deformation where the ground is covered by the vegetations, we need to use L band. So here is an example from Kilauea volcano. The image on the left side is using L band. So which can be, this L band can see through the vegetations, while the right image is using C band, which cannot acquire a coherent interferogram over those forest area. So which we can see here is the forest by a Google Earth image. So before we have talked about how to get interferogram. So from which we can now know how much surface deformation has been created during any pair of SAR images. However, it's more useful for scientists to learn the evolution of surface deformation. So this requires to use multiple SAR pairs to create an INSAR time series. So in addition, creating INSAR time series can overcome some limitations. So using this time series can help us to detect the deformation in a slowly deforming area. And also, since we use DEM atmospheric models, and other models to remove the phase change due to the topography or atmosphere. There must be some uncertainty involved in those models. So by using time series techniques, some of those errors can be removed. So there are different methods we can use to get INSAR time series, such as persistent scatter method, which is usually used in urban area. So it can provide high resolution data in small area. Another popular method is short baseline method, usually called the SB method. The resolution is lower than persistent scatter, but it can be used in a large area, which is suitable for earthquake deformation. The right figure shows a time series data from ACMAC, which is from 2003 to 2008. We can clearly see the uplift history of the ground within the caldera by using this time series data. Okay, finally, I want to show you a table of previous and future INSAR missions. There are more and more INSAR missions happening now than 10 years, 20 years ago. So currently, we can get free data from European satellites Sentinel-1, and in the near future, the US and India mission NISAR will launch and provide us more free data. So with better measurement of ground deformation, scientists can know better how Earth deforms. That is geodesy.